For Unit 12, we're going to be talking about limits and kind of an introduction to calculus. So the notion of a limit is a fundamental concept of calculus, so let's start with the definition. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. The way we read that, let me just zoom in on this. So we say, just kind of like highlighting the part. So we say this part LIM is the limit, and this says as x approaches c. So the limit as x approaches c of f of x, so this is our function, is L. In other words, what it's getting really close to. Now for this part right here, I'm just going to draw a rough sketch of the graph, and your graph might end up being a little different than mine, just because we're freehanding this. So let's just say I go 1, 2, let me space those out a little bit better. 1, 2, 3, 1, 2, 3. And say we've got a curve that starts at 1, 1, and just kind of curves up. Now I'm going to choose a random point here, and I'm going to choose a point, I'm going to say that's like at 1.5. So I'm going to say the limit as x approaches 1.5 of whatever this function f of x is, so this is f of x, is, and then we're just going to say it's getting really close to, well, based on my graph, it looks like it's getting close to 1.5 as well. That was not necessarily intentional, but that's just how it kind of looked. So this is the y value that it approaches. Now, right now, especially these first couple of examples, you're going to be like, well, why do we need this limit thing? Why can't we just plug it into a function? And right now, honestly, you're kind of right. But we'll talk more about why this is appropriate and why this is more useful for for graphs that don't end up looking like this. So we're asked to use a table to estimate numerically the limit as x approaches 2 of 3x minus 2. So let's make a quick table. And I'm going to give you some x values to plug in. Let's just start with 1. So we have x and we have f of x. We'll start with 1. We plug that in. We get 3 times 1 minus 2, which gives us 1. Now let's say we plug in some non-integers. Let's say we do 1.5. Well, if we plug in 1.5, so you got 3 times 1.5, which is 4.5, minus 2 gives us 2.5. Let's say we plug in 1.9. 1.9, so we got 3 times 1.9, which is 5.7 minus 2, which gives us 3.7. Now, let's pretend we don't, let's pretend we don't know how to plug in 2. Again, that seems silly right now, and right now I'd argue that you're probably right. But let's do plugging in 2.1, so just a little bit to the right of it. 3 times 2.1 is 6.3, minus 2 gives us 4.3. Let's plug in 2.5, and 3 times 2.5 is 7.5, minus 2 gives us 5.5. And finally, let's plug in 3. So we got 3 times 3, which is 9, minus 2, which gives us 7. So really, we're looking at this number here. We also need to look at the numbers around it. So at 1.9 and at 2.1, we're at 3.7 and 4.3 respectively. So based on what we see there, we can probably say the limit as x approaches 2 of this function 3x minus 2 is equal to 4. Now, of course, on this one, we could just plug in 2. So this does seem like overkill. But right now, we're just kind of getting used to the format. So talking about this, the properties of limits and direct substitution, which is really what I was just hinting at there. You've seen that sometimes the limit as f of x approaches, or as x approaches c, so in the previous case, the limit as x approaches 2, is simply what we'd get if we just plugged in f of c, or in the previous one, f of 2, as shown in example 1. In such cases, it is said that the limit can be evaluated by direct substitution. In other words, the limit as x approaches c of f of x is just f of c. In other words, what happens if we just plug in that number? Now, there are many we call these well-behaved functions, such as polynomial functions and rational functions with non-zero denominators that have this property. We're just going to practice a couple of these. It's going to be, again, we're just kind of getting used to this format. And then at the end of this next page, we're going to take a look at when it becomes more important. So, for example, the limit as x approaches 4 of x squared. Again, for this one, we can just plug in 4. So we've got 4 squared, oops, sorry, that didn't write down, equals 16. Okay, that seems kind of silly. What I'd like you to do is take a few moments, pause, and do the rest of these, watching out for like the letter C. Pause the video, do the rest of these, and then we'll come back. Okay, clearly you paused, we're ready to rock. So this next one, which is going to be 5 times 4, which is 20. The next one we can just plug in as is. So we got tangent of pi divided by pi. Now the tangent of pi, if you recall that, that is 0 over pi, which is just 0. You can use the unit circle on that if you need. This one, the limit as x approaches 9 of the square root of x, so we just can plug in 9. So we got the square root of 9, which is 3. Letter E, the limit as x approaches pi of x times the cosine of pi, so we end up with x times the cosine of x. I was getting ahead of myself. Pi times the cosine of pi, which ends up being pi times -1, which gives us negative pi. And finally, letter F, the limit as x approaches 3 of x plus 4 squared. So we'll do 3 plus 4 squared. Well, 3 plus 4 is 7. If we square that, we get 49. Now, here's where it becomes more important when we have to talk about limits. So the limit as x approaches -3, and then the equation, the function we're plugging into is x squared plus x minus 6 over x plus 3. So step 1, and this is really what we were doing in the previous steps, try plugging in x equals 3. Sorry, x equals -3, my apologies, since we're using that -3 right there. So if we try plugging in -3, we got -3 squared plus -3 minus 6 over -3 plus 3. Numerator, -3 squared, we got 9 plus -3 minus 6 over, well, -3 plus 3 is 0. So we end up with 0 over 0, which really isn't anything. So what we're going to say is there is no value for f of -3. In other words, it's undefined. Okay, so here's where we start having to work with the limits a little bit more. So if it doesn't work, this goes back to a suggestion that I've had since Algebra 2. If you're stuck, what can we do? We should try factoring. So let's take x squared plus x minus 6 and divide it by x plus 3. Let's try factoring that out. The numerator, we've got x, and if it helps you to think about it as x squared plus 1x minus 6 to help us factor, we've got x plus 3 times x minus 2. So two numbers that multiply to -6 and add to +1 over x plus 3. So when we cross these out, we're left with just x minus 2. Well, that makes it a little bit easier for us to work with. So now we can plug in x equals -3. So when we plug in x equals -3, we got -3 minus 2, which gives us -5. So from there, we can say the limit as x approaches -3 of the function x squared plus x minus 6 over x plus 3 equals -5. Now, if you want to check it out, you can plug in some values that are really close to that x value. So I'm going to check out x equals -2.9. So when we plug that in, we end up with -2.9 squared plus -2.9 minus 6 over -2.9 plus 3. And if you're going to do this on the calculator, that's the way I did it, to be honest. Just make sure you put the whole numerator in parentheses, the whole denominator in parentheses, and I scrolled too far, and you end up with -4.9. You can also plug in, say, like -3.1, and you end up with -5.1. So it's really, really close to that -5, even though there isn't technically a point there.